Cauchy Riemann equations furnish us with the necessary condition for differentiability at a point. Here we are going to take the examples of the few functions in which somewhere Cauchy Riemann equations are satisfied and somewhere Cauchy Riemann equations are not satisfied, but the function is nowhere differentiable. So the first example is, we are going to study the function which is nowhere differentiable. Here I am going to take the function as x minus iota y. Let's check whether Cauchy Riemann equations are satisfied or not. So for that, I am going to find the partial derivative of u with respect to x. So what is u over here? It is x, the real part, and v is the imaginary part, that is minus y. So partial derivative of u with respect to x is 1. And partial derivative of v with respect to y is -1. And these two are not equal. That means the Cauchy Riemann equations are not satisfied. What are the Cauchy Riemann equations? The CR equations are partial derivative of u with respect to x should be equal to partial derivative of v with respect to y, and partial derivative of u with respect to y should be equal to negative of partial derivative of v with respect to x. So the first equation is not satisfied, right? So we say that CR equation is not satisfied over here, since the Cauchy Riemann equation are never satisfied. So therefore the function, this given function f, is nowhere differentiable. So we are saying that if Cauchy Riemann equations are not satisfied, the function is nowhere differentiable, right? Okay, let's consider the another function fz equal to xy divided by x square plus y square, where z is non-zero and is equal to 0 for z equal to 0. It is very clear that this function vanishes on the coordinate axis. Coordinate axis, where x equal to 0, the function vanishes, and if y equal to 0, the function vanishes, right? So at coordinate axis this function vanishes, and at z equal to 0, the partial derivative of u with respect to x and y and partial derivative of v with respect to x and y all are equal to 0. Right, the function is 0 at z equal to 0. So which means from here we can say that Cauchy Riemann equations are satisfied. Yes, both the sides are 0 0 for the Cauchy Riemann equations. So therefore Cauchy Riemann equations are satisfied. Very fine. But if I take the line y equal to x, let's check whether the function is differentiable or not. So limit z tending to 0 on fz minus f0 divided by z minus 0. This will be equal to limit, what is fz? I am writing that. It is xy divided by x square plus y square minus f of 0 is 0 divided by, and taking z as x plus iota y, and because we have taken y equal to x, so I am writing here x. Instead of y we are using x. So this is x square. So the numerator becomes x square, right? And when everything is in x, so here I write limit x tending to 0. So this is equal to limit x tending to 0. This is x square divided by 2x square, that is 1 by 2 into 1 divided by, this is 1 plus iota and 1 divided by x, right? And when x tending to 0, the limit is infinity. That means therefore the function is not differentiable at z equal to 0. F dash 0 does not exist. So in this case, even for this function the Cauchy Riemann equations are satisfied, but if I take the case on the line y equal to x, then the function is not differentiable. But along the line the function is not differentiable. So what we are going to study over here, if we start focusing on the neighborhood of the points rather than the isolated points, many of our difficulties will be solved. So that is why the concept of analyticity is required, right? Okay, let's consider one more function. Here it is written that Even if function is continuous and has partial derivatives that satisfy CR equations, we still not guaranteed differentiability. Very important. We have found such function. If I take fz to be xy square divided by x square plus y square, where z is non-zero and is 0 where z equal to 0, differentiability is not guaranteed. Now this function is continuous at the origin. You can prove this. I have already proved this in the previous videos. You can check from that. This function is continuous at the origin. Right? First point. It is continuous at the origin. Second, let's check the Cauchy Riemann equations are satisfied or not. So partial derivative of f with respect to x at the origin is 0, right? Because fz is 0 at z equal to 0. It is 0, and also the partial derivative of f with respect to y at the origin is 0. So the Cauchy Riemann equations are satisfied. Okay. But on the other hand, if I take the derivative of fz at z equal to 0 along the line y equal to mx, let's say, where m is belonging to the set of real numbers. So here I am writing limit xy tending to 0, 0, and writing the function fz as xy square divided by x square plus y square minus f of 0 is 0 at z equal to 0, and here I am writing for zx plus iota y. Now taking y equal to mx on this is limit x tending to 0, and in the numerator x into m square x square, right? So I'm writing here m square x cube divided by, I'm having x square plus y square, that is x square plus m square x square. So I'm writing here, taking x square common, this is 1 plus m square, right? And 1 divided by, okay, x plus iota y. So this is x plus iota mx, or we can take again x common, and this is 1 plus iota m, right? So if you cancel this, we are having m square in the numerator and 1 plus m square into 1 plus iota m in the denominator. That means the limit is depending upon the values of m, right? So the limit will be different for different values of m. So the limit is different for different values of m, which means what? The limit does not exist. The limit z tending to 0, f of z minus f0 divided by z minus 0 does not exist. The function is not differentiable. Differentiability is not guaranteed. Even the CR equations are satisfied, right? So once again, f dash 0 does not exist. So for the negative character of CR equations has been emphasized. They have been utilized primarily to prove the non-existence of a derivative. So now in the next section, we are going to start the analyticity, where we focus on the neighborhoods rather than the isolated points, right? Okay, thank you. Stay blessed.